Really? Okay, set A.
I don't know. I can't.
Sure.
All right, folks. Let's review these questions as a group. So first of all, what does f of x mean? What does f of x represent? Yeah, the y coordinate or the height. And then what does f prime of x represent? It represents the derivative, which is calculating a slope, and it's the slope of the graph at that point. Okay, in calculus, things get worse or harder before they get better. Yeah, a lot of our calculations will look like that. And then what is the formal algebraic definition of the derivative function? So how do I formally define f prime of x equals? What does it mean, Cheryl? Were you going to say it? Oh, so what's the actual definition? F prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, great. So that's the actual technical definition. That will calculate the derivative of any function at any point, provided that that function is continuous, right? It has to be a continuous function, and then you can use that definition, and you'll actually get an answer. Okay, so then what does that formal algebraic definition mean? So what's the visual interpretation of this? What am I looking at? When we look at this definition, what are we looking at? Yeah, we're looking at a fixed point that we're interested in. So this is our point of interest. We're like, hey, I'd like to know the slope right there. And then what else did we have to put on our picture? Yeah, another point, h units to the right. And so that's the key part, is that we're going h units to the right. So now there's my other point, x plus h. So that gives me my arbitrary point. And then I'm finding a secant slope between those two. So I'm calculating that slope. That's what this is doing, is calculating that slope between my point that I'm interested in and then my arbitrary point, h units to the right. And then what is the limit as h approaches 0 doing to these 2 points? They're bringing them infinitely close together, which means instead of doing a secant slope, I'm actually calculating a tangent slope. So that's the visual interpretation of this definition. You're choosing 2 points and bringing them infinitely close together, which the value of h is approaching 0. Okay, and then in order to find the slope of a single point, you find the slope between 2 points, and then what? Bring them infinitely close. So that's the method called a derivative. That's how you find a slope at a point. Okay, so let's see. Here we are. That's not our calendar. It's definitely not February. Let me go back. We can look at the calendar from last time. Sorry, somehow. Okay, here we are, September 10th. We're doing section 2.4 today. Also, that means section 2.3 was due today. So you have until midnight to turn in 2.3. If you have any questions, please email me or send me a message through the Moore system. And then on Friday, we'll do section 2.5. Ooh, and then we're going to have a test next week. So I'll bring you your practice test on Wednesday. In fact, I have the practice test sitting in my office. Darn, too bad I didn't bring it right now. Suppose I could run there during the break. I do want to get it to you. Speaking of my office, I have only seen 1, 2, 3, 4, 5 of you in my office. So at least I think. So keep in mind that before the day of the test, you have to come to my office at least once. Just come on up there and say hi to me, because otherwise I take 50% off your first test. So again, it's just a threat to make sure that you do in fact come up to my office. So if you haven't come up to my office yet, I would recommend you do it today. Just come up right after class. Just come up there. I just look at your notes, and we're done in like 2 minutes. So make sure that you do that before the day of the test. So what does that mean? We have about 2 more weeks before you have to do that. I would just do it today and get it over with. Okay, so office hours, come see me. I'm going to go get the practice test for you and give that to you. And then the last thing to mention is that we finally can go back to the other classroom. So today is our last day in here, and starting on Wednesday, we're going to be in the other classroom. They finished fixing it up. So I'll see you in the other classroom starting on Wednesday. What else? Maybe that's it. So today we're starting section 2.4. Did everyone grab a copy up here? Okay. And did everyone also grab this, the power rule copy? Okay. And I think I have everybody now. Brandon's here now, right? And is Mia here? No, Mia. Okay. All right. Did I tell you this joke yet? I did tell you those 2 jokes, didn't I? No, I didn't. I told you the why is the math book always unhappy? Because you have so many problems. Okay. How do you keep warm in a cold room? How do you keep warm in a cold room? You go to the corner because it's always 90 degrees. Okay. Well, thank you, folks. All right, so here we go. I thought we would review this now. Now that we're familiar with the derivative, let's look at all of these definitions because there's quite a few. The derivative of a function f at a point x, f of x is the instantaneous rate of change. So that's one definition of derivative, instantaneous rate of change. This is in your textbook, by the way. This is a page in the textbook. So you can always just go to section 2.3 and you can see all these. But in terms of synonyms, we have instantaneous rate of change. The derivative is the slope of the tangent line. So instantaneous rate of change, the slope of the tangent line. The derivative is the slope at that particular point. That's true. And then a function is called differentiable if the derivative exists. So a function is only differentiable if it's continuous. But now what we're saying is if you can take the derivative of a function, we call that differentiable. So for a function to be continuous and differentiable makes it a really nice function. Okay, notation. When we say y equals f of x, then we can either write f prime of x, and that means the derivative, or we'll see this notation, dy dx. We've never seen this together in this class. So let's look at that together for a second. dy over dx. Anyone have a guess what the d stands for? Anyone have a guess what the d stands for? A very natural guess would say that the d stands for derivative. Right? I mean, that would be, what's another guess? Anyone? Differentiable, maybe? Both of those would be good guesses because we're talking about derivatives. So maybe you're saying that stands for the derivative. Oddly enough, it doesn't. The d stands for delta, the Greek letter delta. So that's the Greek letter delta. It's just a triangle. It's pronounced delta. And that means change in. And that means the change in y, the change in x, that's actually the change in y is y2 minus y1. And the change in x is x2 minus x1. So all this is really referring to is slope. So dy dx is actually a perfectly reasonable name for the slope of a function at a particular point. Because you're looking at how far up or down it went compared to how far right or left it went. So the d stands for delta, which means change, which means slope. But we're not just calculating a slope. This is technically the derivative. So in the future, when we see f prime of x, that's the same as dy dx. Okay, what else? Yeah, there we go. The notation that resembles a fraction is called Leibniz notation. So again, Leibniz and Newton both developed calculus around the same time in the late 1600s. And it's more so Newton that used this notation, and more so Leibniz that used this notation. There we go. So what else? Verb forms. We find the derivative of a function, or we take the derivative of a differentiable, or we differentiate a function. So all those words mean the same. You find the derivative, you take the derivative, or you differentiate a function. What else? We use an adaptation of dy to mean take the derivative. Oh yeah, so this could mean take the derivative of f of x. That's a little different. They're saying d over dx of f of x is the same thing as f prime of x. So that's one more synonym for you there. Well, I'll leave that there. It could also be d dx of f of x. That could also mean take the derivative. So these are all three notations that we might expect to see at some point in the work that we're doing. What else? Oh yeah, that was the formal algebraic definition, which we've seen. The practical definition. The derivative can be approximated by looking at an average rate of change or the slope of a secant line over a very tiny interval. The tinier the interval, the closer this is to the true instantaneous rate of change or the slope of the tangent line. Okay, so that's what we've seen. Before we get going, are there any questions from the Moore website? Does anyone want to ask any questions? We just finished section 2.3. So here's 2.3. Were there any questions from 2.3 that anybody wanted to ask about? I'm getting a bunch of emails, not from everybody, but I am getting a bunch of emails, and that's really wonderful. I love getting your emails and replying. Stephen?
Question 6, I think.
So, oh yeah, great. So number 6. This was a little tricky because I can't do it there, but on my computer, I would need to take like a sheet of paper and hold it on the screen and then use a ruler and sketch a line and then looking through the paper, see other points on that line. That would be one way you could do it. Or another way to do it is just real approximation. So let's try this one more time. Estimate the instantaneous rate of change at x equals 1. So I'd like to know what the slope is right here, because x equals 1. So what's the slope? If I were to draw a line right there, do I have a really long straight edge? I'll just use my folder. It's not perfect, but I'll use my folder. So that looks pretty good. And I would need to keep that going. Well, okay, there we go. So I have my line here. What point does it go through? Well, I guess I could call that a point. It's not very good because it's not on the grid. This is definitely on the grid. That's a good point. Or if I continue on there, I've got that point. So at this point, it's just a matter of choosing 2 points that look good to you. I suppose what I could do is choose this point, which is 1, 3, and I could use this point, which is 2, 7. That's acceptable. You're allowed to use the point itself as part of your estimation. So now my slope here is up 4, right 1. So up 4, right 1. Right? Because I go up 1, 2, 3, 4, right 1. So let's just go ahead and try the value of 4. Let's see if it works. And this is, Stephen, thanks for asking this question. This is a fun question because you'll notice Moore says your estimate needs to be within 10% of the exact answer. So if I go ahead and type in 4, let's just see if the program will accept it. Oh, goody, it already did accept it. Well, let's just look. Will it accept 3.9? Oh, no. My goodness, it did not accept 3.9. But so, okay, so let's go back to 4.1. Will it accept 4.1? Yeah. Will it accept 4.2? Yes. Will it accept 4.3? Yes. Will it accept 4.4? Apparently that's what it thinks the real answer is, 4.4. It'll also take 4.5 and 4.6 and 4.7. Yep, and it would even, let's see if it takes 4.8. Yep, it takes 4.8. What about 4.9? Oh, no, not 4.9. So what's the full range of answers that it would accept on this problem? It would accept anything between 4.0 and 4.8. So that's a huge range of different answers that you could have gotten for your slope and typed it in and got the answer right. Now, I'm not necessarily saying that when you get to a problem, just start plugging in numbers until you get it, right? You should still do the process of trying to estimate the slope. But keep in mind that sometimes the computer just is looking for an approximation. So if you got the answer 4, try typing something in a little higher and a little lower. And then if it takes it, go back and say, okay, now why did it take that? What point would I have needed, to get that answer? Stephen, does that reply to your question?
Yes, thank you.
Sure. Then could it have been a fraction? Sure, it could have been a fraction too if you typed 4/1. That would have also, that did not take it. I wonder why 4/1 didn't work.
I don't know, it drove me insane though.
It did not take 4/1. Now look at this little yellow arrow. Oh, it says infinite or DNE. No, that's not it. I wonder why it's not taking 4/1. 4/1 was obviously one of the choices that it accepted. And yet it's not. What if I did 4.1/1? Oh, and it did take that. So wait, did it not take 4.0? Oh no, it did take 4.0. It's taking 4.0 but not 4/1? Okay, well there you go, folks. That's wildly strange that it would not take 4/1, but it will take 4.0. And all I can say to that is just that, sometimes the system is not going to be perfect. Sometimes there could be two different things happening. One is it could be a glitch in the system like that. Why it's not taking 4/1 is very confusing to me. Anyone have any guesses? I have no idea. On the other hand, it could just be that you still need to keep tweaking your answer so that it fits the format that it wants. So that's a good learning lesson. Try the answer as a fraction, try the answer as a decimal. Boy, I'm going to have to really think about that one. What about 40/10? No, it didn't take that either. What about 41/10? That's slightly bigger. Oh, it didn't take that either. And yet that's equal to 4.1, and it did take the answer 4.1. Well, as fascinating as this is, don't know what to say about that. As soon as you hit a situation like that, please email me. I don't want you sitting at home banging your head up against the wall, becoming more and more frustrated and depressed. I'd much rather you just email me immediately, and then I can help out. Stephen, that's a good one. I haven't seen that particular error before. Okay, folks, any other questions you want to ask from the Morse system? Which one? Number 8. Okay, great. Thank you, Sadia. So number 8, use the graph to estimate the value of f prime of 2. This is a great question to review as a group because it's reviewing our notation. We want to find f prime at 2. That means at the x value of 2, what is the slope of the function right there? So again, this is on your computer screen. You could print it out and then you'd have it on a piece of paper and you could draw on it. But if I'm just going to go ahead and draw a line that looks like that. Does everyone agree that that looks roughly like the tangent slope? It's roughly the tangent slope. And so I'm just going to go ahead and choose this point right there. And I could even choose this point because that point is certainly on the graph. So I have those 2 points. That's down to right 2. So my slope is theoretically down to right 2, which is simply -1/1, which is simply -1. So Sadia, I wonder if this is the same issue. Let's see. If I just type in -1, it took it. If I type in -1/1, it also took it. So it looks like that was an error that, Stephen, you experienced on just that problem and not on this one. And again, if you fiddled around with this, you might find that it accepts other values slightly less than 1. That is slightly less than 1. Or maybe even slightly more than 1, like 1.1. Yeah. So there's, again, a range of answers that we'll accept, and you just have to get in the window. Sadia, does that answer your question? Okay. Another one? Thank you, Simone. Number 13, the function graphed above has the derivative is positive on the open intervals. Okay, so a positive derivative means what? The slope is positive, which means the function is rising or increasing. So when is this function increasing? Just between -3 and it looks like a half. Right? Well, I see that that graph is very, very small, but it's only increasing between -3 and it looks like a half. So if I go ahead and type in the interval from -3 to 0.5, I'm thinking that that would accept the answer. Now, should I use brackets or parentheses? Parentheses, because at -3, the slope is 0, which is not positive. And at 1/2, the slope is 0, which is 0, not positive. So let's try it. Submit. Not all questions have been answered. That's okay. Yeah, so I got that half right. So Simone, it looks like the answer for that would be -3 to 0.5. Does that make sense?
And you put it as a coordinate?
Great question. That's not a coordinate, it's an interval. I can see how the two look very similar. A interval would look like this, -3 to 0.5. A coordinate would look like this, -3 to 0.5. Definitely, those two notations are exactly identical. However, from context, they're saying the derivative is positive on the interval -3 to 0.5. So in this case, we're talking about an interval, which means we're looking at a number line from -3 to 0.5. So from context only, we know that they're actually talking about a number line. Whereas if it was a coordinate, they would have said something about a coordinate in space, and it would have been a coordinate. Oh, it's -3. Sorry, so it would have been over here. Yeah, so good question, Simone. Just from context, we know that this means they're talking about an interval, not a coordinate.
So
when you use brackets is if you're including a value, like if I wanted to make this a closed circle, then that would be a bracket. Right. On these particular questions, we're never going to use a bracket because they're saying over here the derivative is negative, so it's negative here and here, and we're not including the point at the very bottom because the point at the very bottom, the slope is equal to 0, and 0 is not a negative number. So we're not going to include the point at the bottom, and we're not going to include the point at the top either, because at the top, the slope is also 0, which is not a negative number. So in this particular problem, you're going to use parentheses here, and you'll also use parentheses here for -infinity through -3, union, and then 0.5 through infinity.
And how do you type in the infinity?
Great question. These are all great questions, folks. By the way, somebody emailed me the correct answer for this, but they used a lowercase u instead of an uppercase u. And I think that fixed the problem. As soon as you used an uppercase u, it worked.
Yeah.
Oh, good. Thank you for confirming. And so how do you type infinity? If you click on this little yellow arrow down, it's going to, first of all, give you recommendations for different automatic buttons. So you can always just use those infinities. Or you can type infinity in as 0, 0. I'm sorry, not 0, 0, 0, the letter 00. So that's -00. And can I make that bigger for you folks? Can you see now? That's there. That's -00, as in the letter O. So that would be -00 to -3 union 0.5 comma 00. So that's how you type in infinity. Is the letter 0, the letter 00, lowercase 00. I feel like we saw that somewhere before. Like, where would we have seen that? Did anyone, do any of you know that you can type in 00 for infinity?
Yeah.
I don't know if I said it in class or if it mentioned it on some website. Well, in any case, now you all know about the down, oh my gosh, did I get it wrong? No, I didn't get it wrong, okay. But now you know about the down arrow. So whenever there's an answer choice, well, not that answer choice. Whenever there's an answer choice, let me go back to like 3 here. There you go. When you click on the answer section, there's a little yellow arrow there, and that gives you lots of tools for how to type in your answers. Well, let me erase that so you can see that. That's not necessarily immediately obvious because, as you'll notice, before I clicked on there, right now, do you see the little yellow arrow? No, it's not there. It's only after clicking in the text box that it then says enter an algebraic expression, and then you can click more. It gives you a full definition of what they're looking for. Okay, this is very helpful. It's telling you what kind of answer they're looking for, and if you click the up arrow, it gives you even more tools for typing in functions, trig functions, and infinity, and so on. Simone, great question. Thank you for asking about that. Just a couple of words, folks. The 00 means infinity, and you'll notice in the preview there, it now says infinity. Yep. Or another one is square root is SQRT, and now you can see that that gives you a square root symbol as well. So there's just two that I know of. So 00 means infinity, and square root SQRT means the square root symbol. These are great questions. Folks, as you're sitting at home and you're about to bang your head against the wall, email me, so that I can respond to your question and bring it up in class so that everybody benefits from hearing these clarifications. Just as a final note, you might be sitting here looking at this software saying, man, sometimes the software is a little frustrating, like I wish that there weren't any bugs in it. All I can say is, this software is a metaphor for life. This is what life is like. It's not just this software, it's all of life. So as you work your way through this class, just always remind yourself, this is a metaphor for life. The way I respond to the software is the way I respond to life. And start playing with that idea that the attitude you have in approaching the software is practice for the attitude that you have when you approach your job or anything else. Okay, well, that's all I have to say. Other questions from 2-3? No? Okay, well, I think that's probably it. Let me see here. That was just using the limit definition. Those were intervals. Oh, that was finding the correct graph. And so on. Okay. Well then, we're moving on to section 2.4 today. Section 2.4 says rates in real life. I could be wrong, but this section is a little interesting because I don't think there's any calculus in it. As in, well, there could be a little calculus. Okay, there's going to be a little calculus. Nope, not even a little. I'm pretty sure that this section is all about just familiarizing ourselves with the language that we'll be using for the rest of the semester. And that's okay. We'll definitely talk about the calculus that's in it. Okie doke. So we're doing 2.4, and I think we'll have time left over that we can start 2.5. So on your paper, do you all see all of these abbreviations that I have listed for you? All of those are the abbreviations from your textbook. Those are all from the textbook. So you've got FC, TBC, TC, AC, MC. On the one hand, do you need to memorize those and know what they are? Yeah, you might as well go ahead and memorize them. But on the other hand, are they that crazy that you couldn't just figure it out? I mean, once you know what we're talking about, we're talking about cost, revenue, and profit. Right? That's the main thing we're talking about, is cost, revenue, and profit. So we really just have to learn a few prefixes, and then we know all of them. So let's see here. I did change mine a little bit. I got rid of the FC and the TBC. Cross those out. You can cross out FC and TBC. Okay, so starting then with TC, total cost. That's the total cost to you and your business, which is always going to be a fixed cost plus a variable cost. What's an example of a fixed cost to your business? Like what's one fixed cost your business could have? Yeah, rent, electricity or utilities, payroll to pay all those pesky employees. That's a joke. So yeah, those are fixed costs. You got to pay those every single month, whether or not you make anything at all. And then what's the variable cost? Yeah, the manufacturing cost. Like how much does it cost to actually make the things that you're doing? So I'm going to put in there materials. All right, so like if we're making pizza, then that would be the actual cost of all the pizza dough that you're going through, the tomato sauce, all the ingredients. And yeah, I see your point there, Celia, about how that's the manufacturing cost, the actual things that you're making. So yeah, okay. Well, there we go. So that's your total cost. What's the average cost? If you wanted to take your average cost of something, how would you do that? What are we even taking the average of? Yeah, of all the costs total. So let's just say, I'm going to make a quick pizza company real quick since I already talked about pizza. And my cost is, I'm just going to say daily, $1,000 a day. That's my fixed cost because I have to pay rent, I have to pay my employees, I have to pay for air conditioning and electricity and all that. And then my cost to make a pizza is actually only $2. So there's my fixed cost, my variable cost. So my fixed cost is the $1,000, and then my variable cost is the $2 per pizza. So if I just wanted to do a couple of examples here, what's the cost to me if I make 0 pizzas? $1,000. It's going to cost me $1,000 if I can't make any pizzas today because I still have to pay rent and all that. What if I make one pizza? What's that going to cost me? $1,002 now? Because I just made one pizza, so that cost me $2 for the one pizza I made. What's the cost of two pizzas? $1,004 now? And let's just say the cost of 10 pizzas. What's that cost going to be? 2 times 10 is 20, so 1,020. So just a couple quick examples of what my total cost is to me. So then going back to the word average cost, what does that mean? Average over how many pizzas I made. So I just take my total cost and I divide it by the number of pizzas that I made. And that's what this formula here is. Q stands for quantity. Q is going to be the letter they use most often to represent the x-axis. So when we talk about the x and y axis, x, y, normally y is dollars and normally x is quantity. So just to make a little mental note of that, normally almost any graph that we look at, the x-axis is going to be represented by Q for the quantity of products that you've made, and the y-axis is going to be dollars for cost, revenue, or profit. Okay, so the average cost means you take your total cost and divide it by Q. So what's my average cost for the first one? Well, that doesn't make any sense. The average cost for 0 pizzas would be 1,000 divided by 0, which is undefined. So that doesn't make any sense. But the average cost for one pizza is you take the cost of $1,002, divide it across one pizza, and one pizza cost you $1,002 to make. That's unfortunate. Whereas my average cost to make 2 pizzas was $1,004 divided by 2. So now that's only $502 to make a pizza. Whereas my average cost to make 10 pizzas is $1,020 divided by 10. That's only costing me $102 to make a pizza. How many pizzas do I need to make to bring my cost down, to something reasonable? Maybe 100 pizzas? What if I make 100 pizzas? Then, let's see, 100 times 2, that's 200. Wait, really? 100? No, that's 2,000. So 2 times 100 is 200. That's 1,200. That would be my total cost. And then, so my average cost for 100 pizzas would be 1,200 divided by 100, which is only $12 per pizza. Now we're getting close to having a feasible business. If it only costs me $12 to make a pizza, how much should I charge for these pizzas? At least 20 bucks, so that I can make some profit on them. What if I'm like a Little Caesars or a Papa John's? How many pizzas do you think I make in a day? Should we just say 500?
Yeah.
Do you think a Little Caesars can make 500 pizzas in a day? Pretty sure. I mean, after all, they're hot and ready. You walk in, you just get the pizza, you leave. So let's say a total cost of 500 pizzas. That would be 2 times 500 is 1,000 plus 1,000. That's $2,000 to make 500 pizzas. And now my average cost for all 500 pizzas is only 2,000 divided by 500, which is a whopping $4. So now this is a good business model for a pizza place. If you can churn out 500 pizzas in a day, which a Little Caesars probably can do, we should call Little Caesars and find out. How many pizzas do you make in a day? Does anyone have any guesses? How many pizzas do you think Little Caesars makes in a day? Do you think more or less than 500? Who says more than 500 pizzas in a day? I think easily. Who thinks less than 500? The rest of you? Let's find out. I'm going to call Little Caesars during the break. Okay, so in any case, you saw now how important average cost is. Average cost tells us on average, even though I'm paying that $1,000 up front per pizza, I'm only looking at a cost of $4 per pizza. And if Little Caesars charges $5 per pizza, they're still making $1 profit. And they've already paid their employees, right? That's amazing. So that's how Little Caesars can get away with it. Okay, so does everyone see now that that's the formula for average cost? The formula for average cost is just the total cost divided by the quantity. That's your average cost. Okay, what about marginal cost? Have we ever used the word marginal before? What about margin? Everybody knows what a margin is? Margin on a sheet of paper? I don't think that's really the same meaning. Do we use the word margin for anything else? What's the margin? That is a business term, right? So what does margin mean? What did you say? Additional, that's correct. For every additional thing that you make, yeah. To marginalize someone, isn't that, to marginalize someone, that makes them, to put them on the edge, that's typically a bad thing to marginalize someone. So anyway, in the business context, the margin or the marginal means for one additional item. And that's what I already have right here. MC is the cost of the next item. So if you just make one more item, what's it going to cost me? In my business model right here, what's the cost of one more pizza? If I just want to make one more pizza, how much is it going to cost me? $2. And that's it. That's my marginal cost. So the marginal cost is just the $2. Because if all I want to do is just make one more pizza today, then it's only going to cost me $2. So that's marginal cost. Now you'll notice the formula, which is marginal cost as a function of how many pizzas I've made, is the total cost of Q plus 1 pizzas minus the total cost of Q pizzas. And that's going to get at the cost of the one additional pizza. We're gonna do examples of that. In any case, the definition of marginal cost, there's two different ways to define it. And I'll go into more detail when we actually get to a problem like that. Okay, so then what are we really looking at? Total, average, and marginal. So we apply all those to cost. We're going to apply all those to revenue, total revenue, average revenue, and marginal revenue. And then we'll apply all that to profit. So total profit, average profit, marginal profit. So we're really just talking about three things: total, average, and marginal. So I just put all that for you on the first screen so that you would have that as a list of different formulas. It's all in your textbook, but I just put it there so you can see it. Any questions before we try some? I think you'll find that on the one hand, this section is very simple. But on the other hand, there's a lot of vocabulary that we have to learn and use correctly. So we still want to really concentrate on what we're doing, because we'll be using these terms for the rest of the semester. All right. Let's go ahead and try it out. And number one, the total cost in dollars to produce Q units of good is given by that function right there. Before we even look at the question, everyone, let's draw a graph. What should I put on my x-axis? What's my x-axis? Yeah, quantity Q. So Q is actually my x-axis. And what should I put on my y-axis? Yeah, money, and I'm going to put cost. So far, does everybody have a nice little sketch of the fact that the quantity is on the x-axis and cost is on the top axis? Okay, now they're saying 7Q plus 4,800. Roughly speaking, what does that graph look like? What is this function? Is it a parabola? Is it a straight line? This is just a straight line, right? Everyone write mx plus b right below it. It's just a straight line. Mx plus b. So we have a y-intercept of 4,800. So everybody come on over here to the y-axis and just give yourself 4,800. And then it has a positive slope of 7, which is really 7 over 1. 7 over 1 x plus 4,800. 48,000, sorry. And so I'm just going to give it a positive slope. I'm not going to go into too much more detail of doing like up 7, right 1, up 7, right 1. I just want us to have a picture of the graph. Why? Because we basically are going to draw a graph for every problem that we do. Why? Because all of you are managers of a company and you need to communicate to your employees, to your board, your committee members, anybody, and a graph is always helpful. Okay, so what's the total cost to produce 600 units? Where's the 600 on my graph? Yeah, just over here somewhere, 600. And they're saying, what's the total cost? So I'm looking for this point on my graph. So what is the total cost? What do I do? Just plug it in, right? It's very basic. We just plug in C of 600 equals 7 times 600 plus 48,000. And so what? That gives us 4,200 plus 48,000, which is 52,200. Did anyone else get that? Okay. So there's my 52. And so my coordinate is 600, comma, 52, 200. Well, that's the end of the problem. Now you might say, Mr. G, I could have done this whole problem in my head by just plugging 600 into that, and I could have just written down the answer was 52, 200. Right? Do any of you feel that way? Like, hey, why did I have to draw a graph? And I could have just plugged it in on my calculator. The answer is 52,200. If you feel that way, I don't blame you. I totally get it. This is actually a very, very simple problem. However, a lot of the calculus work that we'll be doing later is going to require that we have this as the starting point for the problem that we'll actually do. So the calculus problems that we're going to do in this class, it's not just a matter of plugging a number into a formula and there's your number. This is actually what we need. We would actually need a really well-drawn graph in order to then move forward and do the rest of the calculus problem. So this is what I want us to practice doing. I'm sure that all of you would have been very comfortable just plugging in the number and calculating it. But learning how to draw a fairly nice graph is the skill that we're actually talking about. So everybody go ahead and do that for number 2. Go ahead and make yourself a nice little graph for number 2 and work your way through part A. Go ahead and do that right now. You can work with your neighbor if you like. But keep in mind, all of us can just plug 2300 into that function and get the answer. What I want to see is a nice little graph. Very nice. Very nice. Very nice. Very nice. You're going to bring one for everybody. Oh, it's freebie. Oh, good. Just bring it through. Okay, I would do it before you. Just to really get in the habit. Let's go. It's a fly box. Get ready for it. Oh, well, hey, stuff is great. Doing good, also. Yeah. Very nice, right? Good. Nice graph. All right, very good. All right. So everybody would have a graph where they're going to start at 55,000. And then the slope is positive, so we're working our way up. And we know that we're looking for 2,300 units. And would someone please tell me what that ends up being? When you plug in 2,300, you get 67,000.
190.
190. Okay, so 67,190. So our coordinate is 2,300, comma 67,190. Okay, so that's the first problem. Just what's the cost? And it's 67,190. So then what's the second question? How many units can be produced with a total of 91,570? So graphically first, where is the number 91,570 on the graph? Is it on the x-axis or the y-axis? This is on the y-axis. So now I'm going to go up on the y-axis to this value, which is 91,570. And then I come across, so you might have to extend your graph a little bit. Now we're looking for this coordinate, right? Because we're wondering the cost is 91,570, which is way up here. Now I need to find this coordinate, which really means that I need to come back down and figure out that x value, right? So that's what this question is asking. And graphically, this is kind of neat. To be able to look at a graph and follow the x and the y to know what you're talking about, you know you have a cost of 91,570. That's on the y-axis. So you find that coordinate, and then you drop down to the x-axis, and that's the value you're looking for. So we know right now that we're solving for x. We must be. We're solving for x because we're looking for the number on the x-axis. So how do we do that?
Subtract 55,000.
Well, that's true. You could go ahead and do this kind of in your head or on your calculator, subtract the 55,000 from that, and then what? Divide by the 5.3, and that would tell it to you. But what I'd like to see everybody write down, because we're trying to say, when is the total cost equal, when is the total cost equal to 91,570? So you'd write down the formula, C of Q equals 5.3Q plus 55,000. And you want to know, when is that equal to 91,570? So, and then I put a box around it. And now I know that I'm solving this equation. Folks, I'm showing it to you this way because this is how I'm going to solve problems like this when we get to the calculus portion. So we're saying, when is the total cost equal to 91,570? So I start by writing down the cost function, and then I set that cost function equal to the 91,570, and I box this portion to bring my attention to the fact that I want to solve for Q now. And just as Josue suggested, we would subtract off the 55,000 and then divide off the 5.3. And algebraically, that's how you get your answer. So now we'll go ahead and do that. Subtract off 55,000. And that gives us 5.3Q equals, goodness what? What do you get, Josue, when you subtract off the 55,000?
36,500.
All right, and then you divide off 5.3. And what's our final answer, folks? Q is 6,900? All right. So 6,900 units, which is now the number I put on my x-axis. 6,900 units. And now if I really wanted to finish this problem really nicely and beautifully and wrap it with gift wrap and put a bow on top, I would label that coordinate as 6,900, 91,570. And now you'll notice that our graph contains all the information of the entire problem that we just did. The graph contains all the information. Now I know that for 2,300 units, that cost is 67,190. For 6,900 units, that cost is 91,570. I know that my graph has a y-intercept of 55,000. I know that my slope is positive. And now I'm ready with this nice graph to then move forward and do even more, if I wanted to. But creating this graph is so much better than just plugging in a number and solving for x. Now we have a visual representation, and we could start doing more calculus with it. Okay. How about number 3? The total cost to produce Q units of a good is given by that function. What's the total cost, and what's the okay. Now we're doing something slightly different. And we should just go ahead and take a break. Because we're about to try something a little different. Now is a good time to take a break. So everybody, the time is, what, 11:50? Everyone will be back at 12.
Are you still want to go to the practice test?
Yeah, I'm going to go on over to my office and pick it up. Let's see.
Close to 700 pizzas.
As what?
It's close to 700 pizzas. They make 3 million pizzas a day across 4,332 stores.
Uh-huh.
So it's 692 and a half.
Ooh, that's awesome. Thanks, Efren. What'd you say, 692?
Yeah.
That's Little Caesars?
Per store.
Yeah, because they make 3 million pizzas a day, and there's 400 or 4,000. It was
Well, that's wild.
4,332 locations nationwide. 792.
Yeah. Or like
Online, you can get charging.
We just need right here. All right, folks. Let's keep going. First of all, Efren was very kind and he did the calculations and data necessary for us. He found out that Little Caesars on average produces 692 pizzas per store. So that's just the average, that at any given store is making 692 pizzas, which you know means that some stores are busier and some stores are not as busy. So easily some stores are doing over 1,000 pizzas a day, which is just wild. Anyway, Efren, thanks for looking that up. All right, so we're starting to look at this next question, number 3. The first part is very simple. It's just saying what's the total cost to produce 4,500 units. So I'm going to forego the graph on this one, and we just know that if we want the cost of 4,500 units, you just plug in the 4,500, and that's your answer. Does someone already have that for us? 85,650. Okay, so that's the total cost to produce 4,500 items. Now, what I'd like to do right now is look at this question from a couple different perspectives. What's the cost of the 4,501st item? Well, first of all, we already know that just by looking at the formula, right? Because this was our flat cost that we had to pay no matter what, and this is the cost for every pizza that we make, well, for every item that we make. So what is the cost of any one item? $7.70. That's the cost for any one item, whether it's the 4,501st item or the 2,000th item or the 10,000th item. The cost is, since this is a linear function, the cost is always $770 per item. Right? For that item, just that one item. And that's only because this is a linear function. If our cost function was not linear, like if it was a quadratic parabola, then that's not the answer. It's just the answer right now because it's linear. And we know that the slope is up 770, right 1, meaning for every additional item that you make, you're charging $7.70. Okay, but there's two other ways to consider this. The first is that if you want the cost of the 4,501st item, and this is important, this is the definition of marginal cost, so I'm going to write this down. Marginal cost, in this case you do the cost of 4,501 items, and then subtract the cost of 4,500 items. And sit with that for a minute and make sure that that makes sense to you. We're calculating the cost of 4,501 items, whatever it is, I'll just keep saying pizza. And then you're subtracting the cost of the first 4,500 pizzas. And so what are we left with? Just the cost of the 4,501st pizza. Because this is the cost of all 4,501, but then we're taking away the cost of the first 4,500, and that's leaving us with just the marginal cost of the 4,501st pizza. So we would say that this formula is the marginal cost of the 4,501st pizza. Notice that this notation right here, MC 4,501, is very particular. You might even want to put 4,501st. Put a little, what is that? A little ST up there to point out to you that you're just talking about that one, the 4,501st pizza. That's what we're about to calculate. So use your calculator. Plug in 4,501 into the cost function. Plug in 4,500 into the cost function. Get those two different values, and then we'll subtract them and see what that difference is. So in the first case, if I plug in 4,501, that's 7.7 times 4,501 plus 51,000. The cost of 4,501 pizzas is 51,300. Oh, that's wrong. There we go. It is 8,565, 7.7. And then the cost of just 4,500 pizzas is 8,565. And if I subtract those two, what do you get?
770.
Yeah, 770. And therefore, that's the cost of the 4,501st pizza. Now again, this one's pretty straightforward because it's a linear function. Had it been a quadratic or a cubic or something more complex, we wouldn't have already known the answer, 770, by just looking up there. We would have had to do this process. So this is the process for calculating the marginal cost. And in fact, now hopefully the formula on the first page makes a little more sense. If you look at the formula on the first page, actually there's a typo in the formula on the first page. If you want the marginal cost of the Q plus first item, then, wait, marginal cost? Yeah, marginal cost. You would do the total cost of the Q plus first item minus the total cost of the Qth item. So I did have a typo on that first page, folks. That's what the formula should say. You're calculating the cost for one item apart. Okay, this is the non-calculus method. In fact, what I should say is that this formula is non-calculus, because obviously you're just subtracting two formulas, and it's exact. A couple class periods from now, we're going to see the calculus method for calculating marginal cost and marginal profit, and the calculus method is actually just an approximation. It's not exact. It's a lot faster. It's an easier calculation to do, but it's only approximate. So you're not getting the exact answer. You're just getting an approximate answer. Okay, so that's how we calculate marginal cost. Let's keep going. Number 4. The demand for a product is given by the following demand function. So let's talk about this for a little bit. Demand. First of all, what does the D stand for?
Price, right?
Well, very good. Yeah, that's the price per item that you should charge. Very good. You read ahead. I just meant D stands for demand. But absolutely right, Lisette. Q is the units in demand, and D of Q, a little counterintuitive, is actually equal to the price per item that you should charge according to that demand level. So this is not very obvious, but D of Q, even though it stands for demand, what it actually stands for is price per item. So I think that everybody in here has taken an economics class of some sort. And when you look at a demand function, demand goes up, right? Doesn't it? Pretty sure? Or does it go down? What makes more sense? Oh, no, it does go down. Demand functions go down. So here's your demand function. And let's see why that makes sense. And again, let's talk about pizza. Let's say that I was charging $20 per pizza. Then I'm only going to be able to sell so many pizzas. Whereas if I was willing to drop the price of my pizza down to $10, I would be able to sell a lot more pizzas. Right? Okay, so this is just an example of a demand curve. What it says is that humans are selfish, right? We're self-interested. Sorry, self-interested, not selfish. And that if I'm charging $20 per pizza, there's only going to be 200 people in my society who are willing to come out and pay $20 for the pizza. Whereas if I drop the price of my pizza to $10, all of a sudden a lot more people will come out of the woodworks, and there will be more people willing to buy those pizzas because the cost is less. So a demand curve goes down like this. And so what in this particular case the D of Q is equaling, it's computing for me the the price that I should charge in order to get a certain quantity of people. So we might want to write that down. Even though it's right there in front of you, I would write it down again. D of Q is the price I should charge to get Q customers to buy my product. That's just another way of thinking of it. So in other words, if you tell me the number of customers you want to come out and buy your product, D of Q will tell you the price you need to charge. Let's just try that once. Let's say that I want to get, so D of Q equals negative 0.007 Q plus 88. Now, let's just see. What would cost about $88? Probably not a pizza. What's something that would reasonably cost around 80 bucks that you would pay for? Okay, maybe a watch. What else? Oh, clothes. Yeah, it could be like a nice jacket, maybe. Sure, either of those things. Let's say a jacket. I'm going to go for a nice winter jacket, okay? Let's say that I wanted 10 people to show up and buy my winter jacket. How much should I charge for it? So in this case, I plug 10 in. 10 times that is negative 0.07. So negative 0.07 plus 88. That means that I could charge $87.93. If I only want 10 people to show up and buy my jacket, I would have to charge a price of $87.93. Whereas what if I wanted 100 people to show up and buy my jacket? If I want 100 people to show up and buy my jacket, I'm probably going to have to put it on sale. And I'm going to have to charge less to get more people to come out and buy my jacket. So when I plug in 100, I move the decimal twice, and that's negative 0.7 plus 88. Oh, well, goody. All I have to charge now is $87.30. Did I do that right? Am I doing my math right? Are you checking my math on your calculator? That's pretty shocking, right? I mean, just at least in this particular example, how much did I have to drop my price to get more people to come out and buy it? Not very much. just by bringing that price down a very little bit, I was able to get a lot more people to come out and buy it. Okay, so in any case, that's what this demand function represents. Q is the number of people that you want to come out and buy your product, and D of Q is setting that price for you. It's somehow like it knows. That's what the demand function knows. It knows how much to charge in order to get exactly that many people to come out and buy it. Okay, so now let's go back to the question. The demand for a product is given by this, where Q is the units in demand and D of Q is the price per item. If 10,000 units are in demand, what price can be charged? So, in other words, if I want 10,000 people to come out and buy my jacket, then how much do I charge for the jacket? Negative 0.007 times 10,000 plus 88. What does it come out to be? $18? Ouch. Well, that's how much I would have to charge for my jacket in order to get 10,000 people to show up to buy it. Okay, how does everyone feel about that? That's how a demand function works. A demand function is always going to have a negative slope because in order to get more and more and more people to come out and buy it, you have to lower that price more and more and more to capture the interest of more people who don't, maybe there are people who would buy this jacket for $1. And then, you'd have a lot more people show up. Okay, so that's our demand function. I think that's all for that particular problem. Okay, number 6. Is that the next one on your photocopy? 5. Oh, here's 5. Okay. So now we have something slightly more complex. We have a demand function. And is this demand function linear? No, this demand function is quadratic. And that's more to real life. Normally demand and supply are not necessarily linear. They're probably quadratic because people are complex. So your demand function is given by that, where Q is thousands of units and D of Q is dollars per unit. Again, dollars per unit you should charge to get Q people. Now I realize it might not actually be Q people. Maybe there's one person who would buy 2 of them. It's like a gift for somebody else. So if 14,000 units are to be sold, what price should be charged? Well, that's pretty straightforward. We're not even going to do that calculation together. You just plug in the 14,000. And you can do all that on your calculator. Does anyone have that answer for us? What should the price be? Now keep in mind, this is very simple, but there's a lot of opportunity for getting your calculation wrong. So make sure you're using parentheses correctly and that you're typing it in your computer the right way. Computer, calculator. I got a very strange answer. Oh! And now I know why I got a strange answer. Okay, what did I do wrong here? If you type in 14,000, you get a really weird number, right?
Yeah.
Let's look again. It says, suppose the demand function where Q is in thousands of units. So what's my input? Just 14. Okay, there we go. I'm happy I made that mistake because we need to be very careful about how we read word problems. The input is already in thousands. So it's just D of 14. Now that makes a lot more sense. If I plug in negative 14 squared minus 2 times 14, oops, and then 6. All right, did anyone else get 372?
Yeah.
Okay, so did I, and that's dollars. So again, remember here, they're saying here that if you want to sell 14,000 units, the price you should charge is $372. Or saying it the other way around, if you charge $372, then 14,000 people are going to come out to buy your product. Part B goes just the opposite. And I asked that all of you write it down the way I'm going to write it down. There's now saying that the price of $4.97 is set, then how many units can you expect to sell? So what that means is you take your D of Q function, D of Q, which is negative q squared minus 2q plus 596. And we're going to set that equal to 497 and solve that. And so just so you all know, that's how I'm going to write this on the board, is that I'm saying, okay, the price is 497. That means I'm not plugging 497 in for q. I'm setting 497 equal to d of q. So I write down d of q, I set it equal to 497, and I box this equation because this is what I'm actually solving. Now, at this point, folks, this is just algebra. Again, this is not calculus. I'll go ahead and bring the 497 over to the left. We're just solving a quadratic right now, so this is negative q squared minus 2q. What? 596 minus 497. Is that plus 99?
Yes.
Okay, so folks, I can go ahead and tell you that pretty much any quadratic they give you in here, more than half of them are factorable. So this is factorable. That would always be your first guess, is, hey, can I factor this? But by the way, do we want our q squared term positive or negative? We want it positive. So go ahead and multiply through everything by -1, or just change the sign on every term. However you want to think about it. I like to multiply by -1. That gives me q squared plus 2q minus 99 equals 0. Because we need our q squared term to be positive if we're going to factor. Okay, so how do we factor? When you factor, you say, what two numbers multiply to make -99, but add to make 2? Yeah, 11 and 9. So we can factor this now into q plus 11 and q minus 9 equals 0. And so using the zero product rule, this binomial times this binomial equals 0 if and only if either this binomial equals 0 or if this binomial equals 0. And that tells us that once you solve for q, either q is equal to -11, which makes no sense, or q is equal to 9, which does make sense. So in other words, this answer here, q equals -11, that answer is called extraneous. Extraneous means the algebra produced it, but it doesn't make any sense in this problem because you can't sell -11 items. Okay, so how many units can you expect to sell? 9? 9,000, right? Because Q is in thousands. So we can expect to sell 9,000 units. So again, we have to be very careful. The formula is in terms of the whole number 9, but the whole number 9 really represents thousands of goods. Okay. And then last, at what value of Q does D of Q cross the Q axis? All right. How do we solve that one? At what value of Q does D of Q cross the Q axis? How many chucks could a woodchuck chuck if a woodchuck could chuck wood? Doesn't it sound like that? Folks, I would start by making a picture. We know we have a graph where this is Q, this is D of Q, and we know that this is a, what? It's a parabola. Is it facing up or down? The parabola faces down, so our graph looks like this. And we want to find that point right there, right? At what value of Q does the D of Q cross the Q axis? So we're looking right there. And what that means is we're looking for when does D of Q equal 0? I'm going to move on over to here to have some more space. So what does that mean now? Again, the way I'm going to set these up in this class is I take my D of Q function, D of Q equals negative Q squared plus, minus 2Q plus 596. I'll take that and I'll set it equal to 0, and then I'll box it to draw my attention to the fact that that's the formula I want to solve. So, same problem. What do I do first? Yeah, I'm going to factor, and before I can factor, I need to change that Q squared term to a positive. So I'm going to change all the signs. It's Q squared plus 2Q minus 596. Changing all the signs is not very mathematical. Multiply everything, multiply both sides of the equation by -1 so that all the signs change. And now, what two numbers multiply to make 596 that add to make 2? This is not quite so obvious off the top of your head. What numbers multiply to make 596? Now, how can we do this? You could just start dividing, right? Probably the most helpful thing to do is make a factor table for 596. So what numbers multiply to make 596? You start with 1, and then you start counting up. So 1, 2. Does 2 go into 596? Yes, 298 times. Does 3 go into 596? 596 divided by 3? No. Does 4 go into 596? 596 divided by 4? Yes, 149 times. Does 5 go into it? No, that's obvious. 5 doesn't go into that. How about 6? Well, 3 doesn't go into it, so 6 doesn't go into it. Does 7 go into it? 596 divided by 7? No. Does 8 go into it? Well, no. Nope. How about 9? 3 doesn't go into it, so 9 doesn't go into it. Does 10 go into it? No, 5 doesn't go into it, so 10 doesn't go into it. How about 11? 596 divided by 11? No. 12? No, 12 doesn't go into it because 3 doesn't go into it. Okay, so this is becoming a pretty boring activity, right? What would be a better way to figure out what numbers go into 596? You can use your TI calculator, or you can use your Excel spreadsheet, because then you can program it to immediately go through and find all those solutions. Check this out. If I just start a new sheet here, I'm going to type in the numbers 1, 2, 3, 4, and then I'll click and drag. So now I've got all those numbers I can divide by. And then I'll type equals 596 divided by that number. And I'll go ahead and drag that down as well. And now that will show me what whole numbers actually go in. So 4 goes into it, 8 goes into it. Oh, no, that's a decimal. Folks, are there two numbers that multiply to make 596 and add to 2? I just assumed that there would be. But now that I'm looking at it, I don't see any two numbers that go into it. Well, what does that mean? That we can't find two numbers that multiply to make 596 to add to make 2. What does it mean? It's not factorable. Okay, so it's not factorable. All right. Well, then what do we do then if it's not factorable? What are other solutions we could use to solve this equation? You just do the quadratic equation. That would be one way. Or you could go to Desmos and just type it in and then go look for the x-intercept. So x squared plus 2x minus 596. Here's my graph, and I can just go over there and find it right there. Apparently it's 23.434. So that would be our answer without doing any factoring, because apparently you can't factor it. So x is equal to 23.434. Okay, now this is okay, because let's just remind ourselves, what are the methods that we have to solve equations in this class? Well, you could factor, if factoring is available to you. You could use the quadratic formula, which we could still do on that equation, and it should give us 23.434. Or you can simply graph it, and you can look at the x-intercepts. All of these are available to us because you're allowed to use a graphing calculator in this class. So anytime you want to, you could always just graph it on your graphing calculator, find the x-intercept, and that would be your answer. All three of these, if you did those on a test, I would give you full credit. Okay, so what does that answer mean? Let's write it out. They're saying d of q equals 0 when q equals 23.434. So on your graph, I hope you all drew a little graph. What does that mean right there? 23.434. First of all, how many quantity is that? It's not 23. 23,434, right? Because these units are in thousands. Q is in thousands. So what we're really saying is 23,434 what? Units will sell if what? If you charge how much? $0. That's interesting. What we're saying is you have this product, and if you just went out and gave it away for free, how many people would show up? 23,434. That's a really interesting value right there. That's how interesting your product is to society, right? Maybe some people have to work. They couldn't come out and get your free pizza. Some people lived across town. They didn't want to make the drive to get your free pizza. But if you just were giving away free pizza, the most you could expect to get is 23,000 people to show up and take all those free pizzas off your hand. So that's what it means to set D of Q equal to 0. You're finding how many people would take it for free. Okay. But then what, number 6? Yeah, Sela.
So I know how these equations are already formulated, but like for instance, like in real life situations, how do people formulate these equations?
That's a really good question. Data and polls. Pollings, but mostly data. Like, so let's say that a company, they actually just started doing an experiment. They said, all right, we're just opening up our business, and today we're going to charge $20 per pizza. And then from that, they found out that they got this many people to buy it, you know, wherever that is. And then they said, okay, let's offer a coupon, or we'll have a special, and we'll say we'll only charge 18. Then they found out that this many people bought it. And then the more and more data that they get by actually doing experiments or taking polls of people, you know, would you buy a pizza for this much money? Eventually, they're going to get kind of a scatter plot of data. Right? These are all just the data points that they've got through experiment or through polls. And then they say to themselves, well, what equation goes through that data? And oftentimes, it'll just be a linear equation that they get. Or if the data was slightly curved, you know, if it was curved, then they would do maybe a quadratic regression. So ultimately, they take data and then they get a regression line to fit the data. And then that's where these actual formulas come from. Does that answer your question? Okay, folks, that's a great question. I mean, unless God walks up and hands you this formula, it's probably because they took data and polls and then did some sort of a regression to get the line of best fit. And that's where the formulas come from. Great question, Sela. Okay, so we're on to number 6. Yeah? Yeah. All right. So the demand equation for an item currently being marketed is given by this. And Sela, where did that equation come from?
Data.
Got it, exactly. Yeah, no, data. Yeah, we got it from data. It's a line of best fit, and in this case, it's a quadratic. Where D of Q is the money that can be charged, and Q is the thousands of units that can be sold, then if 14,000 units are to be sold, at what price should the product be set? So first of all, folks, I just want to point out, sometimes word problems are not that bad. If you were just to look at this word problem and say, oh man, it's a 4-line word problem, how long do you think it'll take you to solve the problem? How hard is the problem? What's that, Alexis? Yeah, they can trick you. Sometimes a word problem takes a really long time to solve. Sometimes it's really short. And it turns out this one's really, really short. All they're telling us is that we have a demand function, which is this. And they're just saying that if you want to sell 14,000 units, what price should you set it at? So first of all, the 14,000 units, where do I put that number? Am I plugging it in for Q, or am I setting it equal to 14,000?
It could be sold, so I'm going to guess equal to?
No.
No, guess wrong.
So the other one. So let's figure out how to know. It says here that Q is the thousands of units that can be sold. Keyword here, Q is thousands of units. And right here they're saying 14,000 units. So that helps us see that 14,000 represents Q. Also, since it's 14,000, and they're saying Q is in thousands, what are we really saying Q is? Q is actually 14. And what are we going to do with that 14? We're just going to plug it into the formula. So all we're really doing here is just plugging 14 into this formula, and that's all they're asking us to do. Stephen, thank you for taking a guess. Folks, sometimes it is a matter of guessing. You know, you could guess and check. You could try both. You could try one way where you plug 14 in and see what you get. You could try another way where you set this equal to 14 and see what you get. And look at both answers and ask yourself which one is the better answer. In this particular case, though, we definitely are saying that since it's 14,000 units and Q is units in thousands, then definitely Q is 14, and we're just plugging 14 in for Q. So what does that give us? Negative 0.15 times 44, I'm sorry, 14 squared plus 44. Did anyone else get 14.6? Okay. So now that we've done it, let's remind ourselves, what did we just find out? If you charge $14.60, you'll sell 14,000 units. Is that fair? You can say that differently. If you want to sell 14,000 units, charge $14.60. I'd like to go back to Sela's question. I mean, this is amazing, right? I mean, this is like having the omnipotence of God. You're like saying, hey, I really need to sell 10,000 units today. How much should I charge? Well, that sounds like guesswork. But provided you've already done a lot of guesswork and experimentation and polling in the past, you have a demand formula that will tell you, hey, this is how much money I should charge in order to sell this many units. And that's how businesses do it. They say, hey, I want to sell this many units. And so then they do data polling and polling of customers and taking various data, and then they find out these formulas so that they know exactly how much to charge. Okay, so that's it for that question. So now what are we on? Does it go to number 8?
7.
Where's my, oh, there's my 7. Okay, 7, 8, 9. Okay, there's only 3 problems left. Great, let's do number 7. So it says, let the demand function for a product be given by this function. Ah, how nice. It's just a linear function. Isn't that nice? Just a linear function where Q is the quantity of items in demand and D of Q is the price per item that can be charged when Q items are sold. Suppose fixed costs are $2,000 and variable costs are $2 per item. Let's just start there. Suppose the fixed costs are $2,000 and the variable costs are $2. How do I write down my cost function? Just like I did for my Little Caesars example in the very beginning. So my cost of Q units would be
2Q plus 2,000.
yeah, 2Q plus 2,000 or 2,000 plus 2Q. They didn't ask for that yet, but we see that they're giving us the information. We should go ahead and write down the formula. We're just being proactive. So we now have a demand formula, which tells us the price to charge if we want to sell Q items. We now have a cost formula, which tells us how much everything is going to cost us. And now we're saying we're going to sell 95 items, right? Maybe what we're really saying is, hey, over the weekend, I went home, I worked real hard, and I made 95 friendship bracelets, right? That's what I did over the weekend. I'm sure you did something similar. So I've got 95 friendship bracelets. I know how much it cost me, and I know how much I can charge to sell them. So now I can figure out how much money I'm going to make, if any. So let's start with revenue. What's the revenue from selling 95 friendship bracelets? Well, how much are we charging for the friendship bracelet? How do we find out how much we're charging? Our demand function. So our demand function, which is D of Q, which is negative 1.95Q plus 240. And we're going to sell 95 of them. So what price can I charge if I want to sell all 95 friendship bracelets? So what price can I charge? Wow, $54.75. Those are some really high quality friendship bracelets. Now we didn't calculate the revenue yet. All we did was calculate how much I can charge in order to actually sell 95 of them. Because after all, folks, what if I only charged 50? What would happen if I only charged $50? Well, I could sell more if I had more, but I only have 95 friendship bracelets. So if I only charge 50 bucks, what'll happen? I'll sell my 95th friendship bracelet, and then 5 minutes later, who's going to show up at my door? More people who want to buy friendship bracelets. And I'll have to say to them, I'm sorry, I'm all out. Right? So that's what would happen if I charge less. If I charge less, I'm going to run out of supply, and I'm going to have people showing up at my business wanting to buy something, and I'm going to have to tell them I'm all out. Are those customers going to be happy? No. So you have no reason to charge less. If you charge less, not only will you have people show up at your door to buy stuff that you don't have, and so they'll be unhappy, but you didn't make as much money as you could have. So you shouldn't charge less. What if I charge more? What if I charge 60? Then what would happen?
You won't sell all of them.
I won't sell all of them. And I'm going to have 5 friendship bracelets left in my inventory. They're going to sit there gathering dust and potentially going bad. So do you have any reason to charge more? No. That's the magic of the demand function. The demand function is telling you how much to charge to exactly sell the 95. Because if you charge too little, you're going to run out. And if you charge too much, you're going to have overstock. So this is running out, and this is overstock. Are either of those good? Not really. You know, if you've got 95 friendship bracelets, let's sell them all today, and then you're done. You don't have overstock. Nobody was unhappy. Okay, all that said, how do we calculate revenue? What's the formula for revenue? Revenue, go ahead and write this down. This is our definition of revenue. The revenue for selling Q units is the price times the quantity. Does that make sense? That's revenue, price times quantity? After all, if my pizza was $10 and I sell 30 of them, what's my revenue? Yeah, 300. You just multiply, right? Price times quantity. So revenue is always price times quantity. In this particular case, how do we find out our price? Using our demand function. So in this particular case, that's the definition of revenue. If they tell you the price, then you just say P times Q. If they give you the demand function, it's D of Q times Q. Both of those are the definition of revenue. In this particular case, we can go ahead and use the first formula because we know the price already. We just calculated it. The price was $54.75. And how many did we sell? 95. And therefore, we can calculate our revenue. So $54.75 times 95. Did anyone else get $5,201.25?
Was yes.
Super. Okay, so that's our revenue. What was the cost to produce all 95 items? So now we want our cost function. Hey, we wrote that down earlier. We just wrote it down on the fly. We didn't even know they were going to ask it for us yet, but we already wrote it down. It's C of Q equals 2,000 plus 2Q. So what's our cost for 95? $2,190? Yeah. So our cost is $2,190. Our revenue is $5,201. And so the total profit, let's first write down the formula for profit. Profit is what? Yeah, revenue minus cost. So in this case, the profit of 95 items is the revenue of 95 items minus the cost of 95 items. And in this case, we actually do know the revenue. It's $52.01.25. And we do know the cost. It's $21.90. And therefore, we can calculate the profit. All right, $3,011.25. Is that what everybody got? Needless to say, if you could spend the weekend making friendship bracelets and then make $3,000, would you do it? Pretty sure we would all stop what we're doing and make friendship bracelets. I think $3,000 a week is pretty good, right? $3,000 a week times 50. Let's just say you take 2 weeks off for vacation times 50 weeks in the year. That'd be making a comfortable $150,000. I'd make friendship bracelets. That sounds good. Sounds like a good time. Okay, what questions do you have about all this? There's a lot of different formulas, right? There's a lot of different formulas. So what I would probably do first is have a reference sheet that you keep handy and out in front of you at all times, where you have all of these different formulas written down, and especially what they mean. So far we have the cost, we have the revenue, we have the profit, we have the demand function, and we also have marginal cost, revenue. So we have all of those things. Maybe when class is over, I'll sit down and I'll make a reference sheet, better than the one that's on the front page of your notes. And that way, we'll all be looking at the same reference sheet. Okay. Number 8 is a slightly lengthy problem. Let's save that for last, and let's do number 9. Can we do that? Let's do number 9. And then we'll go back and we'll see what we can do in terms of finishing number 8. Actually, maybe you can all just do this one on your own. It says the total cost to produce Q units is given by that function. What's the total cost? And then what's the cost of the 801st item? Let's just jot down how you set up the problem together and let's move on. Because I bet you can all finish this one. The total cost to produce 800 units, how would you find it? What's that? You just plug in the 800, right? So the cost of 800, you just plug in 800. That's all I'm going to write down. You can finish the rest. What's the cost of the 801st item? So again, this is marginal cost. And marginal cost of the 801st item, by definition, is equal to the cost of the 801 items minus the cost of 800 items. So there you go. Everyone, let's leave that one there. You can go back and finish it for homework. That's what they're asking for. And let's take a look at number 8. We have 6 minutes. I think we could finish a lot of this problem in 6 minutes. Okay, everybody ready? Here's our last problem for the day. A baseball team plays in a stadium that holds 52,000 spectators. So everyone start a graph. We've got 5 minutes. With the ticket price at $12, the attendance is 23,000. So first of all, what should our axis labels be? Which one of these is the number of spectators and which one is the cost? Or that is, which one is the price? Yeah, almost always price dollars go on the y-axis. Almost always. If you're ever not sure what to put where, know that dollars almost always is on the y-axis. Almost always. Whereas attendance, so the number in attendance is going to be on the x-axis. So what's that first piece of information? With the ticket price of $12, the attendance has been 23,000. So there's a coordinate. Then they say when the price dropped to $10, you know, either they put it on sale or they had a coupon or they just lowered the price, they found that attendance went up to 26,000. And so far, that's the situation that we have. So again, this is a demand curve. This is a demand curve. the more I lower the cost, you know, let's say I only charge $5 to get into a baseball game, would more or less people show up?
More.
I mean, theoretically, more people would show up, right? Because they're like, oh, it's only $5, let's go to a game. All right, so find a demand function where Q is the quantity. Oh, that's all we need to do is just find the demand function. Well, that's all we need to find is just the demand function. This is a demand curve. The demand function is going to tell us the equation that's going through those points. So folks, if I were you, I'm just going to demonstrate the way I like to solve a problem like this. Visually, I can now calculate the slope visually. My slope is very simple. The slope is down 2, right 3,000. Down 2, right 3,000. I can see that right from my graph that I already drew. Because I'm going down $2 and I'm going to the right 3,000 people. So my slope is -1 over 1,500. Did everyone get the same slope? Of course, you could always write out the coordinates and do the slope formula if you want to. You could say one coordinate is 23,000, comma 12, and the other coordinate is 26,000, comma 10, and then you could do y2 minus y1 over x2 minus x1. You could do all that if you wanted to, but I think drawing it is the better way. Okay, so now we just need to come up with our formula, and I think the best way to do that here is point slope form. Have we reviewed point slope form? I don't think we did. Point slope form looks like this. Given a slope m and point x1, y1, the linear equation is y minus y1 equals m times x minus x1. Does that look familiar? That's called point slope form. It's called point slope. Point slope is handy if you're just given a point and a slope. And that's what we've been given. We've been given a slope and 2 points. So which point do you all want to choose? 23,012 or 26,010? Honestly, it doesn't matter. I'm going to choose 26,010. So 26,010 is going to be my x1, y1, and my slope is -1 over 1,500. So now I'm going to write point slope empty. Writing point slope form empty, I just mean that I'm leaving a blank for y1, m, and x1, because now I'm going to go back and plug all those in. And for my y1, I'll plug in 10. For my slope, I'll plug in -1, 1,500. And for my x1, I'll plug in 26,000. By the way, going back to Sela's question, Sela, if a company only had 2 pieces of data and that's it, this is where they would get D of Q from. All they have is 2 pieces of data, but from that they're going to extrapolate and say, this is our demand function. And they're just guessing that it's linear. Okay, so what do? We have to distribute and then solve for y. So y minus 10 equals -1 over 1,500 x minus, well, actually -1 over 1,500 times -26,000. That's positive. What's 1/1500th times 26,000? What do you get when you multiply -1 over 1,500 times 26,000? I would type that into your calculator. -1 divided by 1,500 times 26,000. Did anyone else get 17.33333333? Yeah, -17.333333. Sorry, positive 17.33333. So 17.3 repeating. And now solving for y, I add my 10 over, and I get y equals -1 over 1,500 x plus 27.3 repeating. Okay, so that's using point slope form to come up with a linear equation to describe a line that goes through 2 given points. Keep in mind now that we should translate all this back into D of Q. So what we're really saying is the demand formula, D of Q, is equal to -1 over 1500 Q plus 27.33333. Can I show you all a really nice trick on your calculator? If you type in 27.3333333333333, and then there's a button called Math. This is my favorite button on the whole calculator. Math. As if that's not obvious. Math. Well, the very first option is frac. If you hit frac, then it converts that into a fraction, 82/3. Anyway, there's our demand function. You could have left it as a decimal, that's fine. You just have to remember to put a lot of 3's. So there's our demand function. Does that look correct according to our graph? Is it reasonable that the y-intercept would have been 27.3 and that the slope is negative? Yeah. Okay, well, folks, again, this section did not have a lot of calculus, but it had a lot of new vocabulary terms that we'll be using for the rest of the chapter. We've covered all the questions. When you come back, we'll start section 2.5. I would go home tonight and try section 2.4. Email me with your questions. As I said, more than half of you still need to come see me in office hours. I would recommend coming with me right now so that you can satisfy that requirement and get full credit on your test. So if anybody wants, let's go to my office. Oh, sorry. Hey, I've got your practice test for you. Allison, Alexis, David. I started writing down something to you as you walk out. Here's the practice test. What was this paper for? We'll do that on Wednesday. Oh my gosh, you actually heard me. That's amazing. I forgot. Is Allison in? Hey, you heard me. That's amazing. Here's your practice test. Yeah. 3122, I think. It's just all the way in the back hallway. Oh, you go. Hang on, Michelle. This way. Welcome. Are you coming around us? Yeah. Oh, good. Here you go, Sadia. Yeah, Sadia. Yeah, there we go. There you go, laptop. Okay. I just need to gather my stuff.